Module 2, Lecture B, Cleaning Columns. By the end of this lecture, you will be able to handle missing values in DataFrames using strategies such as dropping, filling, and interpolation with Pandas 2.3.1 methods. Standardize text and categorical columns by trimming, case normalizing, and mapping inconsistent labels. And convert column dtypes to appropriate numeric, datetime, and categorical types to support accurate computations. Handling missing data. Finding missing values. Before you clean missing data, you need to know where it appears in your dataset and how it is recorded. In tables, missing values may be stored as nulls, empty strings, or placeholder numbers. But when loaded into a data frame, these are usually standardized so they are easier to detect and manage. It is important to treat missing values as unknowns rather than as zeros or blanks, because they influence calculations and visualizations in different ways. For example, recording missing ages in a hospital dataset as 0 would distort any analysis related to patient age. To understand missing values in a dataset, first look at how many entries are missing in each column and what percentage of the data they represent. This broad view helps you spot patterns, such as commonly skipped questions or absent sensor readings. Next, examine specific rows or column combinations to see whether the missing data appears random or follows a pattern. This helps you judge which gaps are acceptable, like missing shipping addresses for digital products, and which are serious, like missing prices. By combining overall counts with targeted checks, you can see where the gaps are and how they might affect your analysis or modeling. When working with missing data, you must look beyond obvious empty or null values and watch for placeholders that really mean the same thing. Real datasets often use entries like n/a, unknown, or special codes such as no phone instead of leaving a field blank. These values should be converted to a standard missing marker, so they do not distort your analysis. By profiling each column and flagging these placeholders as missing, you set up more accurate and effective data cleaning later on. Python code. Finding missing values. Demonstrate how Pandas clearly identifies missing data by creating a very small data table that includes different types of missing markers. Show that, once loaded into Pandas, these various markers are all treated as missing values. Then, summarize how many missing entries appear in each column so you can quickly see where data is incomplete. We begin by importing the Pandas library so we can work with data in a table-like format. This import gives us access to the DataFrames structure, which is central for organizing and analyzing data. It also enables a wide range of data manipulation tools that we will use throughout the script. We create a small dataset using a dictionary with 3 columns: height in inches, weight in pounds, and city. Each column is a list of values, and we intentionally include different markers for missing data. The height column has numeric values and a none entry to represent a missing height. The weight column mixes numeric values with a string that says n/a to show a missing weight. The city column lists city names, but also uses an empty string and the word unknown to indicate missing city information. This example illustrates several common ways that missing data can appear in a dataset. Using the Pandas library, we first create a data frame to organize our data in a table-like structure. The data is given as a dictionary, where each key becomes a column name and its list of values fills that column. This step converts raw, unstructured data into a clear, labeled format. Once in a data frame, the data can be easily manipulated and analyzed using Pandas' built-in tools. This step standardizes how missing data is recorded in the data frame. It replaces various placeholder values, such as text versions of not available, empty entries, -1, and the word unknown, with the built-in missing value marker used by Pandas. By converting all these different placeholders into a single consistent form, it makes the data easier to clean, analyze, and work with later on. We now display the cleaned data table to check how missing values are marked. This visual inspection helps confirm that all placeholder codes have been correctly replaced with a consistent missing value indicator. By reviewing the current state of the data, we can ensure that missing entries are handled uniformly. This verification step is important before moving on to any further analysis. To find how many missing values each column in a data table has, you can first use a method that marks every missing entry with a true value and every present entry with a false value. This produces a table of the same size that simply indicates where data is missing. You then apply a method that adds up these true values in each column. The result is a count of missing entries per column, giving you a quick overview of the pattern of missing data in the table. We begin by printing a short header to introduce the section that reports how many missing values each column contains. Then we display the counts of missing entries, which were computed using a method that checks for missing values and then sums them. This summary shows the pattern of missingness across the entire data table and helps us quickly see which columns have incomplete data. With this information, we can decide where further cleaning or data handling is needed. This script shows how to detect and manage missing values in a Pandas data frame. It starts with a small dataset that uses different placeholders for missing data such as none, -1, and text labels like NA and unknown. These placeholders are then converted into Pandas' standard missing value marker so they are treated consistently. After cleaning, the script displays the updated data frame and reports how many missing values appear in each column, giving a quick summary of the missing data pattern. Choosing dropna or fillna. When you encounter missing values in a dataset, you must decide whether to remove them or replace them with reasonable estimates. Dropping rows or columns with missing entries is simple and can work well when the amount of missing data is small or randomly spread out. However, if many values are missing or the gaps are concentrated in certain areas, removing those records can bias your analysis by overemphasizing the fully complete cases. In large datasets with only a few non-critical missing fields, dropping those rows may have little impact, but as the proportion of missing data grows, this approach can increasingly distort your results. When you fill in missing values, you keep all your data by replacing gaps with reasonable estimates instead of dropping rows. This is especially important in areas like medicine or climate science, where every data point matters, and losing rows weakens your analysis. You might use a constant value or a summary statistic, such as the median age, as long as it reflects how the data behaves in the real world. Each filled value is an assumption about what the missing data could have been, so your choices directly affect later analyses, models, and decisions. When deciding whether to drop or fill missing data, focus on how much information you would lose, where the missing values occur, and how sensitive your analysis is to the assumptions behind filling them. If dropping rows would remove an entire important subgroup, such as all records from a certain year, it may be better to fill those values despite the added assumptions. If the missing values are in a non-essential column, you might safely drop that column or leave the gaps. In practice, you often combine approaches such as dropping rows missing critical identifiers, filling numerical gaps with summary statistics, and leaving some missing values for later. Always record the choices you make so you can understand and explain their impact on your analysis. Python code, choosing dropna or fillna. When handling missing values in a dataset, you can either drop them or fill them in, and each choice has different effects. Using a drop operation removes any rows that contain missing values in the selected columns, which reduces the number of observations, but leaves only complete cases. Using a fill operation replaces missing values with a chosen substitute, such as a default discount, so you keep all original rows. On a small sales dataset with some missing discounts, dropping would remove those sales entirely, while filling would keep every sale and simply plug in a value where the discount was missing. We begin by importing the Pandas library, which is a key tool for working with data in tables. Pandas makes it easier to clean, transform, and analyze datasets. In this script, we use it to create and manage a data frame so we can focus on how to handle missing values in a structured way. We begin by building a dictionary to hold sales data with 3 fields: order identifiers, sales amounts in dollars, and discount amounts in dollars. Each field is stored as a list, and some discount entries are missing and represented by a special missing value. This setup mimics real sales data, where discount information may be incomplete. We then convert this dictionary into a Pandas data frame, so the data is organized in a table-like structure that is easier to work with and analyze, especially when handling missing values. We create a Pandas data frame from a dictionary that stores sales information. The dictionary has 3 fields: order identifiers, sales amounts in dollars, and discount amounts in dollars. Some discount values are missing and are represented by a special missing value. When we pass this dictionary into Pandas, it becomes a structured table that makes it easy to work with the sales data and properly handle the missing discounts during analysis. We start by printing the original data frame so we can see the data as it currently exists, including the missing values in the discount column. This initial view is important because it lets us identify exactly which rows have no discount information. With this clear picture, we are better prepared to decide how to handle those missing entries, whether by dropping the affected rows or filling in the missing values. We use the drop missing values method in Pandas to remove any rows where the discount dollars column is empty. This keeps only rows with complete discount information. As a result, the data is cleaned by excluding entries that do not have all the required discount values. The code reports that the data frame now shows the result after removing all rows with missing discount values. It then displays the updated data frame, which includes only rows where the discount information is complete. This filtered view allows you to analyze the data without any gaps in the discount column, ensuring that only fully populated records are used. We use the fillna method in Pandas to replace missing values in the discount dollars column with 0, meaning that if a discount is not recorded, we treat it as no discount given. This approach keeps all original rows in the dataset instead of dropping those with missing discount values. As a result, we avoid losing data while still handling missing discounts in a consistent way. The code updates the data frame by replacing all missing discount values with $0, and then prints a message to indicate this change. It also displays the updated data frame so you can see that any previously empty discount entries now show 0. This method assumes that if a discount value is missing, it means no discount was applied, so 0 is used as the default value. This script shows how to handle missing data in a sales dataset using a discount column as an example. It first displays the original data, where some discount values are missing. Then it compares two strategies: dropping rows with missing discounts, which keeps only complete records, and filling missing discounts with 0, which assumes no discount and keeps all rows. This highlights that dropping can cause data loss, while filling preserves the size of the dataset. Interpolation for missing values. Interpolation is a method for estimating missing values in ordered data, such as time series, by using nearby observations instead of dropping rows or filling with a constant. It is especially useful when values are expected to change gradually over time, like temperature or stock prices, because it helps preserve the natural continuity of the data. By choosing an interpolation method that matches how you believe the data behaves, you can fill gaps in a way that maintains important context. Tools like Pandas provide several interpolation options to support different assumptions about the data's structure and smoothness. Linear interpolation is a data cleaning method that fills in missing values by assuming a steady, straight-line change between two known points. For example, if an hourly electricity reading is missing, the method estimates it proportionally between the surrounding values. This works best for variables that change smoothly without sudden jumps. Pandas also supports time-based interpolation, which uses actual timestamps for irregular data, and methods that carry the last known value forward or the next known value backward, which are useful when a measurement stays constant until it is updated, such as weight or price. When you use interpolation to fill in missing data, treat the results as estimates rather than real observations and apply it carefully based on your data and goals. Overusing interpolation, especially across long gaps or in highly variable data, can hide important extremes and lead to misleading conclusions. It is usually best to limit interpolation to short gaps. Visually check the results and be especially cautious in sensitive areas like financial risk or environmental monitoring. To maintain data quality, combine interpolation with other approaches, such as dropping records with too many missing values or using simple fills for categorical variables. Python code. Interpolation for missing values. In this lesson, you will learn how to fill in missing numeric values in ordered data using simple interpolation. We will focus on temperature readings over time and compare the original raw data, which may have gaps, with the smoother interpolated values. To do this, we will use interpolation methods from the Pandas library on a small dataset that is indexed by time. This will show how interpolation can create reasonable estimates for missing measurements while preserving the overall pattern of the data. The code starts by importing the Pandas and NumPy libraries, which are essential for data manipulation and numerical work in Python. Pandas is used to manage structured, table-like data through DataFrames, while NumPy supports efficient array operations and mathematical functions. Together, they provide the tools needed for numerical computations, handling missing values, and performing interpolation and data analysis in the rest of the program. We create a sequence of hourly timestamps starting at 8 in the morning on January 1st, 2024, covering 6 hours. For each timestamp, we assign a temperature value in degrees Fahrenheit. But some of these values are missing and are marked as not a number. This gives us a time-indexed temperature dataset with gaps. Later, we will use interpolation methods to estimate and fill in these missing temperature values. We organize the temperature data in a Pandas data frame with one column called temperature in Fahrenheit, which stores the temperature values. Some of these values are missing and are represented by special not a number entries. The data frame uses a time index made from a Pandas date range with hourly timestamps starting at 8 in the morning on January 1st, 2024. This structure lets us manage and analyze how the temperature changes over time, even when some measurements are missing. The code first prints a message explaining that it will show the original temperature data, which still contains missing values. It then displays the full data table of hourly temperature readings, including the gaps. Seeing this unprocessed data makes it easy to identify where values are missing. This initial view is important because it provides a clear baseline for later comparison with the interpolated results. This code uses a Pandas interpolation function to fill in missing temperature values in a data table. It applies linear interpolation, which estimates each missing value based on its position between the nearest known values. The limit direction is set to forward, so it only fills gaps that have a known value earlier in the sequence. This method is useful for time series data, where temperatures are expected to change in a roughly linear way between recorded points. We use the Pandas interpolate method to fill in missing values in a time-indexed dataset. With time-based interpolation, the method looks at the actual spacing between timestamps to estimate the missing points. By setting the limit direction to forward, it only uses known values that occur earlier in time to make these estimates. This keeps the interpolation consistent with the natural order and timing of the data. We combine the original temperature data with the two interpolated data sets by concatenating them side by side in a single table. This creates a new data structure that holds the original temperatures, the linearly interpolated values, and the time-based interpolated values together. We then assign clear column names such as original Fahrenheit, linear Fahrenheit, and time-based Fahrenheit, so it is easy to identify and compare the different interpolation methods. We display a short message to introduce the comparison of interpolation methods, which prepares the listener for the results. Then we show the combined dataset that contains both the original temperature readings and the interpolated values. This lets us visually compare how the linear and time-based interpolation methods filled in the missing temperatures. By viewing them side by side, we can assess how each method estimated the gaps in the data. This script shows how to handle missing hourly temperature readings using interpolation in Pandas. It first builds a time-based dataset with some temperatures left blank, then displays the gaps. Next, it applies two methods to estimate the missing values: a simple linear interpolation based on surrounding data points, and a time-based interpolation that uses the actual time spacing between readings. Finally, it combines the original and both interpolated results so you can compare how each method fills in the missing temperatures. Text cleaning basics: trimming and lowercasing. When working with text columns, it is important to remove irrelevant formatting so the data reflects its true meaning. Trimming gets rid of extra spaces at the beginning or end of text, and converting everything to lowercase makes lettercase consistent. This ensures that values like city names or product titles are stored in a uniform way, so entries that are logically the same are not treated as different. Such standardization is essential for accurate counting, grouping, and comparison of text values, and it helps prevent misleading or distorted analysis results. When collecting text data like country names from an online form, people may type the same value with different capitalization or extra spaces, such as Canada with a space at the end or in all lowercase. Although these look the same to us, computers treat them as different strings. To make the data consistent and comparable, you should trim extra spaces and convert all text to lowercase so these variations become a single, standardized value. The same idea applies to other text fields such as job titles, product categories, and survey responses. When cleaning text data, trimming spaces and converting everything to lowercase are simple ways to improve consistency, but they must be used carefully. In many columns, capitalization does not change the meaning, so making text lowercase is helpful. However, for fields like product codes or passwords, changing the case can corrupt the data. Trimming spaces is usually beneficial as well, but some fields may rely on specific spacing for correct formatting. By choosing thoughtfully which columns to clean in these ways, you can improve consistency without damaging important information. Python code: trimming and lowercasing. This lesson shows how to clean text data in a Pandas data frame by trimming extra spaces and converting all text to lowercase. You will see how these string operations help make text values consistent, so comparisons and analysis are more reliable. A small example data frame is used to illustrate the text before cleaning and the improved standardized text after cleaning. We begin by importing the Pandas library so we can work with our data in a structured way. This gives us access to powerful tools for data manipulation, including creating table-like data structures and performing operations on text. Using Pandas makes it easier to organize, clean, and transform our data for analysis. We begin with a dictionary called raw data that has two entries, one for city and one for country, each linked to a list of names. These names have inconsistent formatting, such as extra spaces and mixed capitalization, to mimic messy real-world data. Organizing the information this way sets it up to be converted into a Pandas data frame. Once in that form, we can efficiently clean and standardize the data for later analysis. We use the Pandas library to create a data frame from a raw data dictionary that holds city and country names with inconsistent formatting. The data frame gives us a clear, structured layout of this information. By organizing the data in this way, we can easily apply cleaning steps to standardize and correct the city and country entries. The code first prints the original data frame so you can see the messy text values before any cleaning is done. This initial view is important because it lets you compare the data before and after transformations. By seeing the starting point, you can better understand the impact of later steps, such as trimming extra spaces or converting text to lowercase. We begin by cleaning the text data in the data frame, focusing on the city column. To do this, we use a Pandas string method that removes any spaces at the beginning or end of each city name. This step trims the text so that all entries are stored in a consistent way. Having neatly cleaned city names is important for accurate data processing and reliable comparisons later on. This step cleans the text data in the country column of a data table by removing any extra spaces at the beginning or end of each entry. It uses a Pandas string method called strip to do this automatically for every value in that column. Cleaning the text in this way makes the country names consistent and helps ensure accurate results. When you later perform data analysis that relies on exact text matches. The code converts all text in the city column of the data table to lowercase. This makes city names consistent, no matter how they were originally capitalized. As a result, any comparisons or operations on city names become more reliable. This step is an important part of cleaning and preparing text data for accurate analysis and processing. The code converts all text in the country column of the data table to lowercase. This standardizes capitalization so that different versions of the same country name are treated consistently. As a result, comparisons and analyses on this column become more reliable. Overall, this step helps keep the text data uniform and easier to work with. We now display the data frame after cleaning to confirm that our changes worked. The output shows that extra spaces have been removed and all text has been converted to lowercase. By printing the cleaned data frame, we can clearly see how the original messy text has been transformed into a consistent format. This verification step is important to ensure the data is ready for accurate analysis or further processing. This script shows how to clean text data in a Pandas data frame by trimming extra spaces and converting text to lowercase. It starts with city and country names that have inconsistent spacing and capitalization, and prints this original messy data. Then it applies Pandas string operations to remove leading and trailing spaces and make all text lowercase, creating a uniform format. Finally, it displays the clean data frame to highlight how the text has been standardized, which is important for consistent analysis and comparison. Standardizing category labels. After fixing basic text issues, an important next step is to standardize category labels so similar items are not treated as different. in many datasets, the same concept can appear under several names, such as different versions of a country's name. If these variations are left as separate categories, the analysis can become misleading. To avoid this, you choose a single clear label for each concept and map all variations to that label. This turns a messy column into a clean, consistent feature that better represents the true structure of the data. To design an effective standardization scheme for categorical data, first understand your data domain and analysis goals. Then examine each column to find unique values and spot patterns such as abbreviations or typos. For example, in hospital data, terms like cardiology, cardio, and card may all refer to the same department and should be mapped to a single standardized label. Always document these mappings, because they represent your assumptions about how values are grouped. These assumptions can change with your purpose, such as merging tablet and ITAD for a broad sales report, but keeping them separate when you need brand-specific analysis. When standardizing category labels, choose carefully which categories to merge and which to keep separate. It is reasonable to combine clearly similar terms, such as single family and house, into single family house, and to map vague labels like other to a consistent label such as unknown. However, avoid overmerging, which can hide important differences, like treating hybrid and electric vehicles as the same, and avoid undermerging, which creates too many tiny categories. Clear, consistent label definitions and rules for edge cases make your data both more powerful and easier to interpret. Python code. Standardizing category labels. This lesson shows how to clean up messy category labels in a dataset by using a simple mapping approach in Pandas. You will see how different text variants that refer to the same thing can be converted into one consistent canonical label. By standardizing these labels, your categories become clearer and more reliable. This makes your analysis cleaner, easier to interpret, and less prone to errors caused by inconsistent naming. The script starts by importing the Pandas library, which is used to work with data in tables. This import lets us use the DataFrames structure and many built-in tools for data manipulation. With Pandas available, we can efficiently clean and standardize category labels in the dataset. This step is important because consistent labels are necessary for accurate and reliable data analysis. We begin by setting up a dictionary that stores messy real-world style data for two fields: country and product. Each field is linked to a list of strings that represent different ways the same label might appear, such as several variations of United States for country and several variations of electronics for product. These inconsistencies are intentional and will later be used to show how to clean and standardize the labels so that all variations map to a consistent form. We begin by building a data frame from a dictionary using the Pandas data frame constructor. The dictionary holds lists of messy country and product labels, and the constructor arranges this information into a structured table. This organized data frame becomes the foundation for our data cleaning and standardization work. Once in this format, the data is much easier to manipulate and analyze in a consistent way. We begin by printing the original categories table so we can see the data frame with its messy country and product labels before any cleaning or standardization. This initial view serves as a baseline that we will later compare with the cleaned version. By examining the unprocessed data first, we can clearly observe the variations and inconsistencies in the labels that our cleaning steps are designed to fix. This makes it easier to understand the impact and importance of the standardization process. We use a dictionary called Country Map to standardize different text labels for the same country. Each entry links a variant of the name United States, such as USA, USA, or US, to a single canonical label, United States. By converting all these variants to one consistent label, we ensure our data uses uniform country names. This makes analysis more reliable and easier to interpret. The code standardizes country names in a dataset by first converting all entries in the country column to lowercase, so capitalization differences do not matter. It then uses a predefined mapping to replace each lowercase country name with a consistent label. If a country is not found in this mapping, it is automatically set to United States. The result is a new column of cleaned country names that is consistent and ready for analysis. We use a dictionary called the product map to standardize product labels by mapping different lowercase text versions to one canonical label. For instance, the word electronics and its shortened forms like elec. And elec are all mapped to the single label electronics. This unifies different text representations of the same product category and keeps the labels consistent. Having this consistency is important for clean and reliable data analysis. The code first converts all product names to lowercase so that different capitalizations are treated the same. It then uses a predefined product map to replace these lowercase names with a single standard version for each product. If a name is not found in the map, it is replaced with the default category, electronics. This standardization makes the product labels consistent and easier to use in later analysis. Now, we display the data frame so we can see the standardized categories alongside the original messy values. This view lets us directly compare what each label looked like before and after cleaning. By doing this, we can clearly see how well our mapping process worked to create consistent, uniform data entries. This script shows how to clean up inconsistent category labels in a dataset using Pandas. It starts with a table that has messy country and product names, such as multiple variations of the same country or product. Using mapping dictionaries, these variations are converted into consistent, standard labels, like mapping all country variations to United States and all product variations to electronics. The script first displays the original messy data, then applies the mappings to create new columns with cleaned labels, and finally prints the updated table. This process produces uniform categories, which is essential for reliable data analysis. Whitespace and symbol cleanup. When working with text and categorical data, it is important to clean up messy whitespace and stray symbols so that identical values are treated the same by the computer. Extra spaces at the beginning or end, multiple spaces between words, or special non-breaking spaces can cause what should be one category to appear as several. Punctuation or decorative symbols attached to values can also split a single category into many. For example, the same city name with extra spaces or a period might be counted as different entries. Proper cleaning avoids inflated category counts and prevents misleading analysis results. When cleaning text data, it is important to remember that some spaces and characters may be hidden or look identical, even though a computer treats them as different. Data from spreadsheets or websites can contain extra spaces, tabs, or different types of dashes that make values appear the same to us, but not to software. To avoid this problem, we normalize the text by converting unusual spaces to standard spaces and different dash characters to a single hyphen. This ensures that values which should match are stored and processed consistently. When cleaning symbols in your data, first decide which characters are meaningful for your analysis and which are just noise. Punctuation or special symbols might matter in things like product codes or social media tags, but can be safely removed in other contexts, such as trailing periods or emojis in labels. If categories like department names appear with small variations, such as added punctuation or icons, they should be standardized so they are not treated as separate groups. By removing unwanted symbols, fixing extra spaces, and making characters consistent, you keep categorical columns clean and support accurate data processing and analysis. Python code, whitespace, and symbol cleanup. This lesson shows how to clean messy text data in Pandas by fixing whitespace and removing decorative symbols. You will see how strings that look slightly different can be standardized into consistent categories. The focus is on using simple replacements to handle spaces, dashes, and extra symbols so that similar values are treated the same in your data. We begin by importing the Pandas library, which is essential for working with data in tables. Pandas lets us create and manipulate structures called DataFrames. In this script, we will use Pandas to build a data frame that holds text data and then clean it. The cleaning focuses on fixing messy whitespace and removing unwanted symbols so the text is ready for further analysis. We begin by creating a dictionary that stores messy text data for two fields, city and department. The city field contains several slightly different versions of New York, such as one with a non-breaking space and another with a period at the end. The department field contains several variations of sales, including one with an exclamation mark, one with extra space, and one with an emoji. This small dataset is designed to mimic real-world text data with inconsistent formatting that we will later clean using Pandas. We use the Pandas library to turn a dictionary called data into a data frame so we can clean messy text values more easily. This dictionary has two entries, city and department, and each one is linked to a list of text strings. By converting this dictionary into a data frame, we can take advantage of Pandas' string handling tools to efficiently manipulate and clean the text in these columns. We begin by printing the original data frame so we can see the raw text data before any cleaning. The table contains city and department values, with inconsistent spaces and symbols, making the formatting messy. Displaying it in the console lets us visually inspect these irregularities and understand what needs to be cleaned. This initial view provides a clear baseline for comparing the data before and after cleaning operations are applied. We create a new column in the data frame to store a cleaned version of the city names. To standardize the text, we first replace non-breaking spaces with regular spaces, since non-breaking spaces can cause inconsistencies in the data. We then replace any tab characters with spaces as well. By converting all these different whitespace characters into normal spaces, the city data becomes more uniform and easier to work with. This step cleans up the city names by removing any periods or commas that appear at the end of each name. It uses a Pandas string replace operation with a regular expression to target these trailing punctuation marks. By stripping out these extra symbols, the city names become more consistent and easier to work with in data analysis. This code cleans the city data in a column by standardizing its spacing. It first turns any run of multiple spaces into a single space, so the text is consistent. Then it removes any extra spaces at the beginning or end of each entry. The result is neatly trimmed text that is ready for further processing or analysis. Here we are cleaning the department column by removing decorative symbols and emojis. We use a Pandas string replacement with a regular expression that keeps only letters and spaces. This strips out all other characters and leaves just the alphabetic text. Doing this helps standardize the department names for later analysis. Here we are cleaning the department column by fixing extra spaces in the text. We first replace any run of multiple spaces with a single space to make the internal spacing consistent. Then we remove any spaces at the beginning or end of each entry. This leaves department names neatly trimmed and uniform, which makes them easier to use in later analysis or categorization. We first print a short message to signal that we are about to show the cleaned version of the data, which helps distinguish it from the earlier, messy output. Then we display the data frame, focusing only on the columns that were cleaned. This lets us quickly see how white space and symbols have been standardized. By viewing these cleaned columns, we can visually confirm that the text normalization worked and that the data is now more consistent and ready for further analysis or processing. We begin by printing a short message to explain that we are comparing unique city values before and after cleaning. We then count how many distinct entries appear in the original city column to see how varied the raw data is. Next, we count the distinct entries in the cleaned city column to see how many similar entries have been merged. Finally, we print both counts side by side to show how the cleaning process has reduced and consolidated the set of city names. This script shows how to clean messy text data in a Pandas data frame so similar entries are treated consistently. It starts with city and department names that contain irregular spaces, punctuation, symbols, and emojis. The code standardizes city names by converting special spaces and tabs to normal spaces, removing extra punctuation at the end, and collapsing multiple spaces into one. It also cleans department names by stripping out decorative symbols and emojis, and then normalizing spaces. Finally, it prints the cleaned data and compares how many unique city names exist before and after cleaning, demonstrating that the process reduces unnecessary variation in the dataset. Converting column types. Numeric conversion errors. When you convert columns that look numeric into actual numbers, you often run into problems because real data is messy. Values like dashes empty strings or markers such as n/a can cause errors or turn into missing values during conversion. A column may mostly contain numbers, but a few cells might hold comments or symbols, forcing you to decide whether to let the conversion fail, treat those entries as missing, or keep everything as text. These issues are important signals about data quality, and recognizing them helps you make better choices and avoid silently corrupting your data. Numeric conversion errors often occur because different regions format numbers differently, using commas, spaces, or periods as thousand separators or decimal points. For instance, a financial dataset might use commas to mark thousands, so 12,500 should mean 12,500. But a system with the wrong settings may treat that comma as invalid. In other locales, a comma represents the decimal point. So 12,5 means 12.5, which can be misread if the system expects a period. These mismatches can cause some values to load correctly while others turn into missing data, which can distort averages and statistical models if you do not check for and fix these formatting issues. When numeric columns are stored as text because of problematic entries, basic operations like sorting and filtering can give incorrect results. This is especially harmful in areas like healthcare, where treating ages as text can distort age-based analyses. Mixing missing values with strings also creates inconsistent error handling, slows processing, and makes the data harder to reason about. By carefully reviewing error messages and using a consistent approach to handling invalid entries, you help numeric columns behave correctly and support accurate, reliable analysis as datasets grow. Python code, numeric conversion errors. In this segment, we will demonstrate how numeric conversion can fail when a column contains messy or invalid values. Using a data analysis library, we will convert a column of strings to numbers and see how invalid text entries are turned into missing numeric values. We will then compare the original string column with the converted numeric column side by side to clearly show which values were successfully converted and which became missing. This helps you understand how data cleaning affects numeric fields with problematic entries. The script starts by importing the Pandas library, which is used to work with data in table form. In this context, Pandas creates a data structure called a data frame and allows the code to perform various operations on it. One key task is converting values stored as text into numeric types. Pandas also helps handle any errors that occur during this conversion in a controlled way. We begin by building a dictionary that includes a sales dollars entry containing a list of strings that look like numbers, but also include irregular values such as n/a and a question mark. These strings are meant to represent sales figures, but they are not all in a clean numeric format. We then use this dictionary to create a Pandas data frame, which organizes the data into a structured form. This data frame will make it easier to manage the sales values and later convert the string entries into proper numeric data. We use the Pandas library to create a data frame from a data dictionary. This dictionary has a key for sales in dollars, whose values are strings that look like numbers, but some are not valid numeric entries. The data frame arranges this information into a table, which makes it easier to work with. This structure is especially useful when we later try to convert those string values into proper numeric data for analysis. We begin by showing the original values in the sales dollars column to establish a baseline view of the data before making any conversions. A PRID statement displays a short descriptive message followed by the values from this column. These values are first converted into a standard Python list using the toList method, which makes them easier to read and later compare with any transformed versions. We convert the sales dollars column into a numeric format using a Pandas function that turns each entry into a number. During this process, any values that cannot be converted, such as text placeholders, are automatically replaced with a missing value marker called nan. This ensures the new sales numeric column contains only valid numbers or clearly identified missing values. As a result, the data becomes cleaner and easier to analyze. We now display the converted numeric column by first printing a short message to indicate that we are showing the transformed values. Then we take the values from the sales numeric column of the data frame, which holds the results of turning the original text entries into numbers. Any values that could not be converted are stored as missing values, or nan. Listing these values lets us quickly see which entries were successfully converted and which ones failed. To check how many values in the sales numeric column failed to convert from the original strings, we look for missing values, which appear as nan in Pandas. We use a method that marks these missing entries and then count them to get the total number of failed conversions. Finally, we print this count to see how many entries could not be turned into numbers, which helps us understand potential data quality problems in the original column. This script shows how to handle numeric conversion errors in a Pandas data frame when a column contains strings that look like numbers, but also includes invalid entries like n/a or a question mark. It first displays the original string values, then converts the column to numeric data while forcing any conversion errors to become missing values, represented as nan. After the conversion, it prints the new numeric column so you can see which entries failed to convert. Finally, it counts and reports how many values turned into missing data, indicating how many inputs were invalid. Date-time parsing formats. When working with date and time columns, you must correctly interpret the text format so each value is converted into an accurate date-time object. Datasets may use different orders for day, month, and year, and may represent time with different clocks or time zones. If you do not give clear parsing instructions, tools can misread dates, such as confusing March 4th with April 3rd, which leads to errors in time-based analysis. Careful and consistent parsing is essential to avoid these mistakes and protect the integrity of your data analysis. Recognizing common date and time patterns helps you control how parsing works and avoid confusion. Different datasets may use various separators. Change the order of year, month, and day, or switch between compact and more descriptive formats. Time values can also vary in how much detail they include and whether they specify a time zone. By clearly defining the expected format, you reduce ambiguity and ensure that all valid values are converted consistently. When working with datasets that contain inconsistent date and time formats from different sources, it is important to standardize the raw strings before analysis. You may see full timestamps, simple dates, or text-based month names, sometimes with errors. To clean these, choose a clear parsing approach, apply it consistently, and then review any values that fail to convert. Examine the remaining unique patterns, decide which formats you will support, and treat the rest as missing or fix them manually. This careful standardization helps avoid misaligned timelines and misleading trends in your results. Python code, datetime parsing formats. This lesson shows how to use the pandas to datetime function to parse different kinds of date and time strings. It explains that relying on automatic parsing can lead to ambiguity when date patterns look similar, such as when it is unclear which number is the month and which is the day. By explicitly specifying the exact date format, you remove this ambiguity and make the conversion more reliable. The comparison between automatic parsing and using a defined format highlights why explicit format strings are safer for consistent date-time conversions. We begin by importing Pandas, a powerful Python library used for data manipulation and analysis. This import gives us access to tools for creating and working with data structures called DataFrames. Using these tools is essential for handling and parsing datetime strings in our example, since Pandas provides built-in functionality to manage and transform date and time data efficiently. We begin by creating a list of date strings that are written in several different formats. For example, some dates use month, day, year. Others use year, month, day. And some use day, month, year. One date is also written in a more verbose, wordy style. This variety of formats will be used to show how the Pandas library can correctly interpret and convert these different date strings into standard datetime objects. We begin by creating a Pandas data frame to organize our data in a table-like structure. In this case, we use a dictionary where the column name is raw date and the values are a list of date strings stored in a separate variable. This approach lets us load all the raw date strings into a single structured column. Once in a data frame, these dates are easier to manipulate and analyze using Pandas data handling tools. We start by printing a short message to let the user know that the original date strings are about to be shown, which sets up a clear comparison with the parsed dates later. Then we display the raw date column from the data frame using Pandas. By turning off the display of row indices, the output focuses only on the date values themselves, making it easier to visually compare the original strings with their processed versions. We use Pandas to automatically convert date strings in a data frame column into datetime objects with the toDatetime function. By setting the errors option to coerce, any values that cannot be parsed become a special not-a-time value instead of causing an error. The day first option is set to false, so the first number in the date is treated as the month, which matches common United States formatting. This automatic parsing is convenient for handling many date formats without specifying each one, but it can misinterpret dates when the format is ambiguous. We create a mask to find date strings that use numbers separated by dashes. This mask checks each value in the raw date column and marks those that contain a dash. With this information, we can later apply special parsing rules only to those entries. This helps us handle different date formats correctly and consistently. We define a date format where the month comes first, followed by the day and then the year. This format is used to parse date strings that follow this exact pattern. By specifying it, we remove ambiguity about which part is the month, day, or year. This allows us to reliably convert matching date strings into datetime objects. We apply a specific date format only to certain rows in the data frame. First, we identify rows where the date strings contain dashes, which suggests a numeric date pattern. For these rows, we convert the strings to datetime objects using a month, day, year format, relying on the Pandas date conversion function with an explicitly defined format. Any values that cannot be converted are set to missing, so we only keep dates that match the expected pattern. We now display the data frame to compare the results of automatic and explicit datetime parsing. After printing a short message to describe what is coming, we show the full data frame without row indices, so the focus is on the values themselves. This lets us clearly see how the original date strings were interpreted by the automatic parser versus the parser that uses a specified format. By viewing them side by side, we can easily spot any differences or errors between the two parsing methods. This material explains how a script uses Pandas to parse dates written in different formats and why this can be tricky. The script first shows the original date strings, then lets Pandas automatically convert them to dates, which can cause mistakes when formats are ambiguous, such as a numeric date that could mean either March 4th or April 3rd. To avoid these errors, the script explicitly specifies a month, day, year format for numeric patterns and applies it only to the rows that need it. Finally, it compares the automatically parsed dates with the explicitly parsed ones to reveal differences and emphasize the importance of defining date formats for accurate datetime conversion. Efficient categorical types. When a column represents categories, converting it to a categorical type can greatly improve both performance and clarity. This format stores a compact list of unique categories with internal codes, which reduces memory use and speeds up many operations. It also makes it clear that the values are specific groups rather than arbitrary text. In large datasets, such as transaction records, this distinction can turn slow, cumbersome analysis into a much smoother and more efficient process. Categorical types improve data consistency by letting you define a fixed set of categories and, when needed, their order. This is especially important for ordinal data such as satisfaction ratings or education levels, where the order has meaning. Using categorical types ensures that sorting and comparisons follow the logical order of the data instead of a simple alphabetical order. They also help reveal data quality problems, because any unexpected labels become obvious and can be investigated and cleaned up rather than silently accepted. Using efficient categorical types is important because it tells analysis and modeling tools to treat certain columns as groups rather than as continuous numbers. This makes tasks like summarizing revenue by customer segment or region faster and easier to interpret. In predictive modeling, clearly separating numeric and categorical predictors also prevents mistakes, such as treating category codes as real numeric values. Overall, converting appropriate columns to categorical types improves performance, preserves the structure of the data, and leads to more accurate and understandable results. Python code. Efficient categorical types. This section explains how to convert text columns into efficient categorical types to improve data handling. It highlights how categorical columns use less memory than standard text or object columns. It also shows how defining an order for categories allows meaningful sorting, which is especially useful for ordinal responses such as ratings or levels. We begin by importing the Pandas library, which is a key tool in Python for working with structured data like tables or spreadsheets. Using Pandas gives us access to the DataFrame structure, allowing us to manage and analyze tabular data efficiently. This setup is important because we will use it to convert text columns into more efficient categorical types. Doing so helps reduce memory usage and supports meaningful sorting of data that has a natural order. We begin by creating a dictionary called data to hold our sample information. It has two entries, one for payment method and one for satisfaction level, each linked to a list of text values. The payment method list repeats categories such as card, cash, and check in different orders, while the satisfaction list repeats levels from very dissatisfied up to very satisfied. Together, these lists form a small example of categorical data with repeated text values, similar to what we often see in real data processing tasks, and they will later be converted to more efficient data types. We begin by creating a data frame with the Pandas library, which organizes our information into a table. This table is built from a dictionary where each key becomes a column name and its list of values fills that column. Using this structure makes it easier to manage, view, and analyze the dataset in later steps. We begin by checking the original data types and memory usage of the data frame to understand how the data is stored and how much memory it consumes. We look at the type of each column to see whether it is stored as an object or another data type. Then we compute the total memory usage in bytes, using a detailed option that includes the memory taken up by the objects themselves. This gives us a clear baseline to compare against after we optimize the data frame. We convert the payment method column of the data frame to a categorical data type to save memory. Categorical types are more efficient than generic text types when many values repeat. This works by storing each unique payment method once and then mapping each row to one of these categories. As a result, the data frame uses less memory while preserving the same information. We create a list called order that defines the sequence of satisfaction levels from very dissatisfied up to very satisfied. This ordered list establishes an ordinal scale that reflects increasing satisfaction. We then use this list to convert the satisfaction column into a categorical type that respects this hierarchy. As a result, sorting and analysis based on satisfaction levels will follow the intended progression from least to most satisfied. We create a new column in the data frame called satisfaction category by converting the existing satisfaction values into a categorical type. We define the categories in a specific order, from very dissatisfied up to very satisfied, to represent an ordinal scale. By marking this categorical data as ordered, we allow the values to be sorted meaningfully according to this progression. This lets us treat satisfaction levels as ranked stats rather than just separate labels. We now examine the data types and memory usage of the data frame after converting some columns to categorical types. a message is printed to indicate that we are viewing this updated information. The data types for each column are then displayed, including the new categorical columns. Finally, the total memory usage of the data frame in bytes is calculated and printed, using a deep measurement to more accurately reflect the true memory consumed by the underlying objects. We sort the data frame by the satisfaction column after converting it to an ordered categorical type. This lets us arrange the rows according to the defined sequence of satisfaction levels, from very dissatisfied up to very satisfied. Organizing the data along this ordinal scale makes it easier to interpret patterns and to analyze or visualize satisfaction in a meaningful order. We begin by printing a short message to explain that we are about to show the data frame sorted by satisfaction categories, so the output is easier to interpret. Then, we sort the data using the satisfaction column, which has been set up as an ordered categorical variable, so that the sort follows the natural order of satisfaction levels. After sorting, we display only the satisfaction and payment method columns, highlighting just the information that matters for this example. This script shows how converting text columns in a Pandas data frame to categorical types can improve efficiency. It starts with payment method and satisfaction columns stored as generic text, then reports their data types and memory usage. The payment method column is converted to a categorical type, which lowers memory use. The satisfaction column is converted to an ordered categorical type that reflects its ordinal scale, making sorting meaningful. After conversion, the script prints the new data types and reduced memory usage, then sorts the data frame by satisfaction to demonstrate how ordered categories enable logical ordering. In this lecture, you learn to handle missing values in data frames using strategies such as dropping, filling, and interpolation with Pandas 2.3.1 methods. Standardize text and categorical columns by trimming, case normalizing, and mapping inconsistent labels. And convert column dtypes to appropriate numeric, datetime, and categorical types to support accurate computations. In the next module, Module 3, we will go over transforming data.
Thank you for your attention. See you all in the next lecture.